Good afternoon, everyone. I am Prasant Mishra. I am coordinating this webinar series that is aimed at skill development programs for students. As per my position in IEEE Bangalore Section goes, I am the current treasurer for the section, and I spend a lot of time in volunteering for activities for the benefit of students and the community at large. So, as part of this webinar series for skill development of students, we have organized two lectures since the beginning of this particular program. This is the third lecture, and in fact, it is the second lecture in the course of data and decision engineering. So, the first lecture was on Monday, wherein the fundamentals of machine learning was delivered to participants. This lecture, which is the second one, will build on that, on those fundamentals, and will do a deep dive into applying data and decision sciences and engineering to the field of robotics. Okay. So to deliver this particular talk, we have Dr. Anima Majumdar. She is a scientist at the Innovation Labs of TCS Bangalore. Anima holds a PhD in computer vision from the Indian Institute of Technology in Kanpur. Before joining her PhD program, she was a senior software engineer at Robert Bosch, and since then she has taken computer vision and robotics as a domain of interest and pursued deep science and research into it. So without much further delay, let me hand over the stage to Anima. Anima, up to you. Please take it forward.
Yeah, thank you, Prashant. Thank you for the nice introduction. So I'm audible to you, right?
Yes, Anima, you're audible.
Okay. So okay, this is a post-lunch session. I hope I will not bore you with too much of theories. So this session I have divided into two separate parts. In the first part, I will give a brief overview, or you can say a basic understanding of what is neural networks and what is deep learnings. And in this next session, I will go through some of our applications in deep neural networks for robotic work that we have performed in TCS Innovation Lab. So I'll go with this part, neural network and deep neural network. So first, I'll say I'll start with the very basic of neural network. Everybody may be knowing, everybody may have some understanding of neural network. So at least people have heard that neural networks, it is everywhere in artificial intelligence. So what is neural network? What is neuron? So I'll start with that very basic. So neurons or neural networks is an information processing technique. It is inspired by biological nervous system, the way our human brain works. So consider there is a single neuron. The blue color nodes you can see, this is a single neuron, and we have some inputs like input in the form of a vector x, and there is a bias term called b, and this neuron will come and it will be multiplied with the associated weights of each of the component of that vector, and then a bias terms will be added. And once that bias terms is added, we will use some non-linearity, or we will use some activation function to get the output. So now, if you think about a simple math, like why we need to use a term bias term into it. So basically now, suppose w into x plus b, that if you see that straight line equations, if b term is not there, or mx plus b term is not there, generally the straight line will not pass, it will always pass through the origin. So, but in real life, our functions may not pass through the origin always, right? So for that, we introduce in neural network, we always introduce the term bias. So I'll just go into the details of the single perceptron. Perceptron is the basic building blocks, the way we say the cell is the basic building block for our skin. So perceptron is also a basic building block of neural networks. So we have to understand it first in order to understand in depth of neural networks or deep neural networks. So Now that, as I told, now we have input vectors. It can be image, it can be speech, it can be any other data. So if you have an input vector of m dimensions, and each input vector is associated with the weights like W1, W2, W3, and Wm, we multiply it with each and every component of the input, and then we add a bias terms. And after that, if you say there is a sigma function, and after the sigma function, we do some nonlinear activation into it. So nonlinear activations, there are many reasons behind why we need to use nonlinear activations. One of the reason is that because we have, if we don't use nonlinear activation, it will act like as a simple regression. Can we go to the next slide? Yeah. So now, okay, first, before going into that advantage of activations function, I will just tell you, like, generally what kind of activations functions are being used. Now, to start with a simple activation function, there is a function called sigmoid function. If you see the sigmoid function, the first one from the right, so it is like an L shape. So it generally it will start with that 0, starts with 0 and end at 1. So it ranges from 0 to 1. So one thing is like it has been used in many places, but one disadvantage with this approach is that, like, because it is starting with 0, so like if you divide it into, say it is not actually addressing the negative input, negative these things. So now what we are saying, so we are using 10h function. So it will cut in the middle, like the middle portions, 0 will cut in the middle. So we can go from -1 to +1. So in many cases, this 10h function is more advantageous than this sigmoid functions. But one problem with this other initial two approaches is that if you see the tails, the upper tails, as it is approaching to 1 or -1, so it is flattening. So when it comes to generally, I'll explain in later. Generally, what we are doing is we need to perform some, we have to get some derivatives in order to learn those weights. So when we get the derivative of this, like these functions, so those regions where flattening is happening, it will be vanishing, like it will, derivative will not be there. So in those cases, it will be difficult, the derivative will be 0 and it will be difficult to update the networks. So later that another this recent one, that another activation function came, that is called ReLU. It has been widely used in deep learning and neural networks. So ReLU, what it is doing is, for negative, generally, it will give input as zeros, and for positive, it will get input as X. So there are various variants of ReLU. So this, the primitive one was this one. So next slide, please. So as I was telling, like activation function has got various advantages. One of the advantages is that when we use this that, as I said, that perceptron network without activation function, it acts as a linear regression model. So now suppose there are some networks we want to see like outcome as either 0 or 1. So we want to say class 1 or class 2. When we want to get this kind of classes or multiple this kind of classes, so we need to have probabilistic outcome. So if we use sigmoid function or ReLU function, so that will help us in getting probabilistic outcome. So another thing is that if we don't use, or if we use only linear activation function, that Wx plus b, those things, or some other linear activation functions, so there are certain situations, real life situation. For example, I'm showing here 3 different pictures. You can see from left, if you see, so there are red dots and there are green dots. So those dots, if I am asked to separate those dots, if I draw a single line, straight line, no matter what, if I add on or change those lines in various directions, I am not able to separate those green and red dots. But when I use nonlinear activation function, the thing is when it is learning the mapping, when it is a nonlinear function, in the last one you can say, so a complex nonlinear function it has learned and it is able to separate those green dots from the red dots. So that is one of the important reasons why activation functions are being used. Next slide, please. So here I will just again I'll give details about this, how it is working and all. So now, for example, we have an input vector, small vector, of x1 and x2, and we have weights. So associated weight is also will be of same size, like weight is 3 and minus 2 WO. So now when we are performing the operation, like when it is passing through the summation operation, what it is doing is it is multiplying this weight with W, it is taking a dot product and then it is adding the weight. Once the weight is added and after the dot product has been done, we are passing through a sigmoid function. This first sigmoid function, as I said earlier. So this outcome we are saying, like if you see that outcome before passing the sigmoid function, the outcome is something like this. The function is something like this: 1 plus 3x1 minus 2x2. So now suppose it forms this one, forms a straight line. You see is in the graph. So suppose one input has come, suppose minus 1 and 2, one input has come. So it is falling in one of the parts. So similarly, there are so many inputs may come. So like the way it is separating this, learning those lines. So now that you have, when you perform this sigmoid function, you got the outcome as probability value 0.002. So our outcome is supposed to be near to 1. Then we will say, okay, it is predicted well. But it is coming out to be 002. So what could be the reason? Because we have just we have just performed the forward pass. The network is not learned. It has just initialized some weights and then it has got the input vector and it has performed that forward operation and got that value. So now that this network has seen that, okay, this value is there and we want, because initially when we are training, we need to have our known input and known output. There are, as you might be knowing, when it is coming, when it comes to like machine learning or these learning things, there are normally two different types of learning. One is supervised learning, another is unsupervised learning. So when it comes to supervised learning, so we need input and we need output. So this neural network, these things comes under supervised learning. When we are training, we need to know the output. So if our desired output is 1 in this case, and we are getting output as 0.002, so this is not at all acceptable. So for that, we need to perform some updating operations that I'll show you how we are doing it. But before that, I'll show this is the simplest neuron that we have said. This is a single neuron at small input and the sigmoid functions. So now if we want to do an outcome is only 1, either 0 or 1. So now if we want to perform multiple tasks with this perceptron, how we are doing it, we can increase the number of nodes. Number of neurons, suppose Z1, Z2, outcome is Y1, Y2. So we can keep on increasing, but yet it is very simple because this, even though the function it is learning, so simple that in normal cases, where in real life scenarios where the functions are so complex, it cannot address in many cases. Next slide, please. Yeah. So now, how this is how people have addressed multiple tasks or complicated functions. So this is one of the very old approach that people have came up in, I think, in the year 1998 or something. So this is called multi-layer perceptron. So it is a little complex than the previous one. what it is doing is we can have multiple layers now. So this node, that by we started with a single node neuron, now we can have multiple neurons. There can be one input layer that so you can say the single perceptron, like you can multiply it so many inputs, and then there is another layer get introduced that is called hidden layer. So why it is called hidden layer? Because if we say something is hidden, like something we cannot directly see the outcome. If we put a probe on it, we can see the outcome, but otherwise directly we cannot see the output. So there can be multiple hidden layers. One hidden layer, two hidden layers, three hidden layers, so many hidden layers can be there. So how actually it is, with a simple example, I'll show how operation has been done. Now suppose we have got a feature vector like of 4 dimensions, x1, x2, x3, and x4. And every component of that vector will be multiplied with a component of the weight. Weight also will be of same dimension, 4-dimensional vector. So now after this, as previously I have told, after this multiplication operation, it has to the second layer nodes, it has to go through activation function. So it has gone through the activation function. That outcome is A1, A2, A3, and A4. And then, okay, before going to the activation function, after this multiplication and summation operation is done, we are also adding a bias term, because we need to take care of this, that line should not always pass through the zero center. So now that we have got various activation functions at various hidden nodes. So this hidden node is again an input to the last layer. So this input again, it will act as a it will multiply with weights, like then now W2, W21, W23, like it will be there. So once it is again added, and again another bias term will be added, and then it finally will pass through another activation function, and then it will get the output. So generally earlier people have been doing long code for this. Now because we have got Keras, we have this TensorFlow and all, it is a very simple. We can see in the right side there is a small code in it, how you will just write MLP in 4 lines. So you have got input, you will set the dimension of that input. You have got hidden layer. First you can keep on sequencing the hidden layer. Here I have shown only one hidden layer with dimension of 4, and then you have got output of one node. So a model has been created with input and outputs. So next slide, please. Yes. So now that, okay, we know there are artificial neural networks and deep learning like CNN, convolutional neural networks. So like still we want to know like actually how they are working, like what is the purpose of what are the difference between these two. So first I will say like what is this, as you have seen Perceptron, you have seen MLP. So what actually it is doing? So what it is doing, like it actually constructs the mathematical functions that ties together it ties like very simple elements like neuron, as you know, and it finally it is able to make some decisions, like whether it will fall to which class and all. So if you see, the networks can be 2 different networks, like one can be shallow networks. It can be of 3 layers, like as I have shown, multi-layer perceptrons. And another is deep networks. So if you see, this MLP is still a shallow network. Then deep network is how deep it is, like it has gone many layers, much say 100, 200, 400, even more layers are there. So when it comes to that kind of layer, computation also becomes so much. And another problem with this, normally when we use many layers, it encounters a problem called vanishing gradient, that I will tell later what is called vanishing gradient, and why we need this gradient information. So now that we are performing forward pass, I have shown you that we are performing the forward pass. Though now it is getting the inputs and getting the weights, making the decisions. But when decision is failing, what it has to do? So it will back propagate the errors, the input and desired input and the actual input based on it will compare both, and it will back propagate the error as a loss. And then how it will back propagate, I will also go in the next slides. Next slide, please. Yes. Okay. So, okay, before that, I'll just tell now what it is doing, this many layers, like when if you say deep neural networks, what exactly it is doing. So people in computer visions or image processing, so the way they have been, what we have been working earlier, so how we have been working now, suppose there is an image, what we used to do, like we used to extract certain features like age, corners and all. Based on those features, we have to infer some decision kind of things. But that was not at all enough to understand an image, kind of image, like say, for example, a face. Or even for a car or those things like complex faces, the way deep neural is working now, it can able to perform various complicated tasks using this DNN. So what it is doing, if you see, we have multiple layers like layer 1, layer 2, layer 3, layer n. So many layers are there. So when we are giving input, we are giving this vector, x vector, as pixel values. Now you know that images are nothing but some set of pixels. It is arranged in two-dimensional space. So now you can say, if you give these images as a vector, as you can say, because in CNN is handling two-dimensional vectors. So initially, those weights, when we are updating or training those weights, it tries to learn certain basic features like edges, corners. You see in layer 1, it is a kind of visualizations, how it is learning the features. So if you can visualize those corners, edges, or some big features, it is learning. If you have gone through some wavelet kind of thing, somebody have understanding of those, they can see it looks very similar, like the way it is learning those features, like various directional features it is learning. So, and as we go up in the layer, it is learning more abstraction of features, and also it is trying to correlate, like say for example, earlier it was learning corner and these things. Now it is trying to learn an eye, an eyebrow, or a nose, those things. But these are still separate. So as we go even higher into the network, it is actually able to recognize a face. So this is how our deep neural network is working. This is one of the examples. So next slide, please. Yes. So now I will say, like, okay, so you got the gist, like how actually deep neural network is working in a sequential manner. I'll say, like, what are the steps in neural networks? Like it is conventional neural network also, deep neural network also. These are the basic steps. There are 6 basic steps. First step is initializations. We initialize the weights applied to each all the neurons. Then we do forward propagations. As I have told you that for MLP and for Perceptron, we perform the forward propagations and make some decisions. And then we get the error because we have our desired output. We got our output after forward propagations. So we got the error. So to update or to learn the model, so now we have to perform back propagation. Back propagation is one of the very important area for neural network, because this is where we are actually learning the networks or learning the weights. So once back propagation has been done, so we are updating the weights. So this process, this now suppose for we can say there are various ways how we will perform back propagations. We can perform back propagations on every individual input vector, or we can perform batch wise. So once the weights are updated for one individual vector, we can we continue same process for next. We continue till we get the convergence. We get no more the weight are getting updated, or we get reasonable loss, that loss is not falling so much. Or we have to, I'll tell where to stop, like there are various criteria where we have to stop those updates. You can feel free to ask question anytime, because that time that it will be more interactive. Sometimes I have a feeling that I just want to know how much I'm able to convey. If you have any doubt or if you have any question, you can feel free to ask me during the session.
So participants, I think this is happening in audio broadcast mode, so you may not be able to unmute and ask, but please
Okay.
key in your response in the chat window. Anima and myself and Chengappa, we are constantly monitoring the chat window. So any questions posted over there, it will be taken up.
Okay. So now I will go into that loss function because I have covered these forward propagations. So now before going into the back propagations, we have to know the loss function. So now given an input is a simple example, given an input vector, say 4 and 5 components of the vectors. So we have our predicted outcome as probability value as 0.1 and actual outcome is 1. So we have to we have to calculate the loss. So how we are calculating the loss? Next slide. So there are various ways of calculating loss. One of the ways, now suppose given we have a feature vector x and we have outcome as a fx and desired outcome is y. So we do one thing is we calculate the errors for all the input vectors, all given in the data sets. And then we take the average loss. Then this loss is minimized. This is one of the approach that is called empirical loss minimizations. So one problem with this loss minimization is that it is computationally very intense when data set is too big. Next slide. Next slide. Prashant, next slide.
Are you not able to see this? This is the this slide 51.
Yeah, 53, slide 53.
Oh, okay, sorry. Okay, sorry. Yeah.
Yeah, yeah. So now you can see there are so many types of losses. One of the losses you can say regression loss. When we are performing operation like regression operation, so we are calculating regression loss. So there are various kind of ways like to perform regression loss. One is mean square error loss, another is mean square logarithmic error loss, then absolute error loss. And when it perform binary classification, generally people use cross entropy loss. Then hinge loss is there, square hinge loss is there. And for multi-class classification, we also can use multi-class cross entropy loss and KL divergence loss. So these are the various loss functions we have used. So lots of studies are there in these directions, and we have to wisely choose the loss function. Sometimes we have to change based on our applications. So I have given one citation here. You can go through actually this site, like people have been using so many losses, like you can see how people are using various losses. Next slide. Yeah, here I'll show one like how we are using mean square error. So now given input feature vector x and our outcome is fx, this is a kind of regression function. So what we are doing is, and your desired outcome is y. So we are calculating that mean square error of each and every component, and then we sum over those components. And then for all the entire vectors, we calculate the loss. So in TensorFlow, you can use a single line of code to perform this operation. Next line. So now when it comes to binary operations, when we want to perform this binary classification test, so outcome is something like fx as I've shown here. So it will give some probabilistic output. So what it is happening now, suppose you have got two different distributions. Now suppose y is one kind of distributions and fx is one distributions. So we want to merge these two distributions. Once these two distributions are merged, then our losses are minimized. So this is an approach that people they have been using. This is one of the very old approach, and still it is widely used. That is called cross entropy loss. So this tries to minimize the distance between two distributions. So next slide, please. So now that, okay, we have found out this loss function. So next question is how to minimize that loss functions. How we'll get them lesser loss values as we to train the model, was training the model. So now the thing is that there are two ways. Like one is that we need to update the weights. We have to repeatedly updating the weights till the weights are very low, small values. So now weights are nothing but say W as I have shown here. So now this loss, given a loss function, so we want to get the weight value or the optimal weight value with W star where our output is the desired, close to the desired one. Next slide. So there are various approach people have been using to optimize. There are one conventional or classical optimization approach where gradient descent is one of the promising area people have been using since many decades. Another way you can use like genetic algorithms or swarm optimizations. There are very other different optimization approaches which are inspired by biology. So now I will not go into those GA and all those approaches, but I will concentrate on simpler this optimization approach, that is gradient descent. So what is gradient descent? So if we see mathematically, it's a technique that modifies the parameter of a function to descend from a high value of a function to a low value by looking at the derivative of a function with respect to each of its parameters and seeing which step via which parameter is the next best step to minimize the function. Now suppose, so given a terrain kind of structure here, you can see, so you have a weight initialize, you have to initialize the weight. This is a kind of plot of the weights. So you have to initialize those. So this loss function, this is a loss function plot. So now initialize the weight and you have to go step by step in such a way that the loss, you reach to the minimum loss criteria. So after that, the loss will be like very minimal. So how to use those stepwise minimization, or what step you have to do? Like what is this gradient descent? Like gradient descent means normally if you go descent means in opposite direction of the ascending. It was going up loss, you have to minimize, you have to go minus, you have to use the negative sign of it or negative sign of the gradient in a way. So given a loss function, we calculate the gradient and then we take small step for every small this gradient we calculated and keep on updating the weights based on the our loss we have got. Next slide, please. Slide number 58. Yes.
Anima, this is slide number 58.
Yes.
But there's a question here. I think let me just read out the question to you.
Okay.
Mr. Ravish is asking, how will you address the local minima?
Okay, yes. So now here I'll have some slides to show you how to address the local minima. But generally, if you see with this gradient descent or those methods, this has a drawback. If we see like based on the steps we are taking now, say for example, I'll show you in the next slides. I have some slides to show how we are going to address those local minima. That will be more clear. So I'll answer you that question later. So now I'll just say here now this is a simple algorithm how we are performing this gradient descent. We initialize the weights randomly, then we compute the gradient, and then we update the weights. So now we have this again may answer your question partially here. So you have got new weight. You have new weight. It is updated based on the old weight, and then you have the minus sign here, and there is a term called eta. And then we are getting this partial derivatives of those loss functions with respect to each and every components of the weights or the parameters, we can say. So now this, when we are taking the derivatives of the weights, we are getting the steps, right? So eta is the one which is controlling the steps. So based on the eta value we are taking, so here it is saying, okay, how much to move ahead. Now, if we say, for example, if we take the value as too high, so it will jump first. There are certain situations it will skip the local minima, but it will fall in certain regions that it may actually may not come to the global minima also. But again, if we reduce the eta value or learning rate, we call this as learning rate, if we reduce the learning rate so small that it may toggle, that if you see there are certain regions where it is very local minima, full of local minimas, so it may toggle and it may never reach to the global minimum. So this is the one of the problem with all these learning approaches, how wisely we have to choose those learning rates. I think I have partially answered your question. Next slide. Yeah, you are in the correct slide. Yes. So you have to go up actually, 59. Yes. So now I'll just, because back propagation, everybody might have heard about the term called back propagations, but at a time, if you go with these algorithm or mathematical structures, it looks very noisy and we can get confused. So in order to avoid the confusion, I will just explain it with a very simple way, with the simplest possible neuron. So there is a single neuron as an input, and there is an input vector x, and there is a associated weight W1. So now, when this input neuron is there, Z1, and then weight W1 is there, in the input X is there. So it has performed the operation as I have said for perceptron. Then it has got again another, for output terms, we have got another weight W2, and it has given W2 output as a Y hat. So now you have got output as a Y hat, and you have got JW, you have calculated that loss. So you are calculating the gradient with respect to W2. So because you have to update both the weights, it's not only W2, you have to update W1 also. So now if you take derivative of JW with respect to W2, it will not be enough, right? You have to, because it will not we cannot take derivative of W with respect to W1 just like that. So you have to follow this partial derivative. So we keep on deriving till we reach to the initial weights. So this is how it is working. Like this is what we call back propagation method, where we are calculating all the losses till we go to the initial weights. So this looks very simple when we are using a single node. When you use multiple neurons or when you use multiple layers or deep learning kind of structures, it becomes very crazy, like to calculate the back propagations. But if we understand the simple back structures, then it becomes easy. So once we have propagated, so now we have calculated the errors, and next part is how to update those errors. As I have shown in previously in that gradient descent methods. So what we are doing, given weight, initial weight, and then given learning rate, and given that derivative values calculated, so we are updating each and every weight components. So I'll not go into the details of this algorithm. Next slide, please. Yes. So this is what I was telling, like as the question was being asked, like what happens when function is not so smooth, or what happens the function is not convex. In general, the functions are not convex. The functions can be like this, something like this. So when we say you need to reach to the global minima, the lowest possible point, and if you have this kind of functions and you have initialized a point, so there are various tricks you have to think, like how to initialize a point. if you wrongly initialize a point, it may fall into some position from where it may not come back. So we have to wisely, there are various ways people have been using now in the deep neural networks to how to initialize the weights. So if you see, like there are some transfer learning methods also. We use some pre-trained model to fine tune our networks, and this is one of the approach how we initialize our deep neural networks. So as I said, other than initializing the weights, next one is how wisely you are choosing your learning rate, or how you are, it need not be a fixed learning rate. You, based on your data or based on your applications, you can choose adaptive learning rates. There are various kinds of adaptive learning rates people have been using. Next slide, please. Okay, so now this is very interesting, because this, why I'm focusing on all these things is because this you will often face when you are going to work on any of the visual deep learning based projects, because all neural network, all about neural network is how to set the learning rate, how to choose the loss function, and how to initialize the weights. These are very tricky and these are very challenging. So now the amount that the weights are updated during training is referred as the step size or the learning rate that you know, like learning rate I have been referring. So learning rate is a configurable hyperparameter. Generally people choose it between 0 to 1. If you choose 0, it will not update at all. So it will be in between 0 to 1. It should not be 0. If it is too, so it controls how quickly we adapt the model. If it is too large, will reach very fast. But again, I said it may reach to a suboptimal solution. It may never reach to the global minimum. So next is, if we take a very small value and it will toggle, it will reach to a local minima, and it may never reach to the global minimum. So there are various tricks you have to keep trying, or there are trial and error methods, and you have to use some adaptive learning rates. So I have just shown with a graph here. You can see when it is very high learning rate, it will loss is so high, and it has gone to some point and it has struggled. It never reached to this global minimum. So even it is too low, also the same problem. So you have to wisely choose the learning rate, and there are many paper on it. There are many other documents and other tutorials you will get how to choose the learning rate, and also it is very application dependent. So there is not a specific answer to it. Next slide. So now you see, okay, as I have told, I'm just saying some of the names of the adaptive learning rate. Here it is now, one of the is that Adam, another is RMS probe, ADA delta. So these are some of the examples. In TensorFlow, you will get readily available codes are there, functions are there. You just plug in those functions and change the parameters, and you can make use of it. There are some papers I have cited here. You can use those, see those papers also. So you can go through this. Next slide. So because gradient descent is one of the very important area, and people have been still using individual gradient descent is the approach people have been using, though there are some variations in gradient descents. So how the people are using with slight variations, I'll just tell this one. So as I have told you earlier, now suppose I have got a weight initially randomly set. So, and then we have got our inputs, and we have computed the loss, and over the entire loss, we have computed the loss for the entire data. So on that entire data, we have got the average loss, and then we have updated. But when it comes to real life, when we are handling the big data, huge data, when we say we have to compute the gradient for entire data set, it becomes very computationally intense. Sometimes it becomes near to impossible even with these GPUs. So now people moved ahead. So now another approach is that here is, instead of computing a loss for all the entire set at a time, so you can also choose each and every component and calculate loss for each and every component and keep on updating. Again, problem is that here computation is not high because we are computing gradient for each and every input. But the thing is that it becomes very noisy. So when it comes to an accuracy also falls. So people have come, it's not that very old, it's recently in a few years back, people have come up with, after the introduction of deep learning actually, people have come up with mini batch stochastic gradient descent. So what it is doing is, it is taking a reasonable set of images or input vector, say for example 10, 20, 30, 40, these are called mini batches of inputs. So for that each mini batch, it is calculating the gradients. So when we are taking this 10, 20, 40, it is not very big and system is able to actually compute. So, and also another thing is it is also smoothing. So noise thing is getting removed. So, and this is how, this is, it has become actually very efficient. So there are some other methods also, other variants also you can go through. So these are the some basic methods I have told. So with this high performing GPUs, and we can actually perform very fast training using this mini batch stochastic gradient methods. So next slide. So now another problem with this training. So now people have been, now when you will train a neural network, you will often come up with this problem, is a term called overfitting. And you might be knowing in machine learning, convolutional machine learning, people have been saying about regularization terms, regularization. So what is regularization and what is overfitting? So I have just put a simple example here. Now suppose you have got inputs, two different classes. So one is circle and another is cross. So now you have to fit a function. You have to learn a function. So when you are learning a function, so if function is too linear, you have seen that function is too linear here, the first one left, first from the left. So it is not able to address many of the class objects or data. So it comes under underfitting, or it is the results are not at all satisfactory in these cases. So this we call as an underfitting. So now again the right side, if you see, so it has learned so complex functions, so it is going and in many ways, so it is able to address all the points during training. So problem is that when you are fitting in such a way, you are learning a very complex function, and when something new feature comes or new data comes, which is slightly different from the data you have trained, so it cannot address. So though it performs very good with the training data, it performs 100%, near to 100%, but when it comes to testing data, it performs very poorly. So we also don't want this kind of fitting or more function learning. So what we want, a function to learn so that it can also address the new data, even though there is small error with this, but it is still acceptable. So we learn that we call appropriately fitting. So the middle one, there is the function which is properly fitting. There can be some outliers or some features we may not actually address in real life as well. So we have to ignore those data. So next slide. So I will just give an example like how deep neural networks are used actually taking care of these regularization. One of the approach, now suppose you have seen, you have got multiple layers, or with MLP you see 3, 4 layers. One of the approaches, now you currently what I have shown is like we are connecting each and every inputs to each and every nodes of every layers until the output layers. What if we randomly remove some of the nodes, or if randomly initialize some of the nodes while training? So in that way, by doing so, we avoid this problem of overfitting. So it learns a function when we randomly do this, or the term is called dropout. We set some probability value and which probabilistically or randomly choose some of the nodes to drop out at a certain period of our training, and we learn the mapping. So it actually helps in generalizations, and people have got very good results with very various applications, vision and all other applications. So it has found to be very promising. So next slide, please. So another one is, now suppose when you are training a model or training a neural networks, what we see, the loss function, we are plotting the loss function. So this is what I'm showing here. So red color, and that this red color is my loss function, and then when we validate with our validation set, so we also plot that loss. When we see, if we keep on training, see the red color, we keep on training, and it trains for so longer time, and validation error goes high. So we have to wisely choose, and the person who is training for certain application, we have to see where to stop. So early stopping is one of the very good option to avoid this overfitting or to address the unseen data. Next slide. So, so far it was all about conventional neural networks, and it was also applicable to deep neural networks because this was common to all. But what is the difference between these conventional neural networks and deep neural networks? So this is called convolutional neural network, and what the term says, convolution operation is being performed here, and why we call it convolutional neural network. So now we can see, like people have been hearing, it has been very influential since I think 2012, 13, and now till now it has been widely used. We have got variants of convolutional neural networks. Here in few slides, I'll just say what are the components of convolutional neural networks, what are the basic building blocks of the convolutional neural networks, and how new architecture has come, and what are the small changes happened while people are getting newer or deeper and deeper architectures. Before that, I'll just say, like, okay, what are the different applications people could able to address? Earlier, we could able to say, see, even simple operations, performing a simple operation or segmentation of an object, it was very difficult. People were using very complicated algorithm with full of mathematics, even were not able to address segmentation properly in various scenarios. But when convolutional neural network has come, so many things has happened, like it looks like very miracle to us. Some of the like image classification, object detection, semantic segmentation, face recognition, and even for self-driving car, like people are able to perform these depth estimation, they are able to understand the scene, and many more. So it is very interesting to know like what other components are there in the convolutional neural network. Unlike MLP, multi-layer perceptron, so here some additional things are also there. Say for example, here I have an input image, and I have got different layers here. So first we are having given input image, as we are giving directly pixel values as input image, and pixel it is taking, it is also keeping the spatial correlation intact. In a sense, instead of taking each and every single values as a vector form, it is taking 2D component as input. So it is taking like it is having information of its neighborhood data. So now it has got this input data, and it is have initial feature layer. So now it is performing with some weights, given initial weights, again in the form of 2D, and those weights it is performing some convolutional operations. And then one convolution is performed. Now that size is too huge, and we have to reduce the size, and we have to learn the abstractions of the features, or we have to understand more deeper level of features. What we are doing is we are performing operation called subsampling. So there are various name of this subsampling. One of these called max pooling, mean pooling, average pooling. So this kind of pooling operation we are performing. I'll tell in detail what are those pooling operations are. So now we are performing the pooling operations. So we are getting smaller feature maps. So these feature maps again are associated with some weights. So when we are going higher to the another layer, we are again performing some convolution operations. And then we are getting, after convolution has been performed, again we are doing some subsampling using this pooling operation. So you can see, visualize those, how the structure or 2D component has been getting reduced. But again, we can see the feature layer, the number of words, as you say, we are increasing in that dimensions. So now, finally, we have got again some 2D and many 2D blocks of 2D features. So after this, finally, as we go deeper, finally we perform, like we concatenate those features, we get flatten out. We can say we can flatten out those features, and we get a vector, and then it acts like an MLT, multi-layer perceptron, as I have told earlier, like input layer, one hidden layer, then output layer. So it performs multi-layer perceptron kind of operations, that is called fully connected layer. Next slide, please. So I think I have almost explained those operations here, as I told in the last slides. So here also one thing that we have to do is we have to add bias term here as well. So I'll move to the next slide. Yes. So you can see with a simple convolution operation. So if you see how convolution has been performed. So now you have a patch of an input. Instead of taking one input component, we take a patch of a component, say 1, -1, -1, -1, 1, 1, this kind of this 3 cross 3 patch. So now we have got, suppose the weight as 1, 1, 1, 3 cross 3 patch. So what we are doing is we are multiplying each and every, the way we are performing this dot product. So we have taken, and we have averaged out. So this is what is called convolutional operation happening. So basically, for each and every, as we are sliding the window, we have taken a window at the middle of the point, the middle point of that input has been replaced with the convolution. After the convolution outcome, whatever we have got, it has been replaced with that value. So next slide. So now once you have replaced with that value, this is again another example. So in a complex scenario given, now suppose we have got images of M cross N, and you have got, after convolution operations, you have got certain outcomes, certain values. So you have to you have to reduce the size of the features, as well as we have to take the effective features. So better features, better represented features. So in order to do that, how people are performing pooling operation. So how pooling operation has been performed, if you say, so if I got 2 cross 2 patch, if you take, so in the 2 cross 2 patch, first one, the circled one, 1725 is there. So max pooling, what it is doing, that in that patch, it is just replacing that 4 values with the highest value. So it has taken 7 out of all 4s. So if we move to the next patch, it has taken out of this 3, 9, 5, 12, it has taken 12. And similarly for the next one, it has taken 6, and the last one, it has taken. So once you have performed max pooling for this, the bigger one, it has reduced by 6, this smaller patch of 2 cross 2, and yet it is able to retain the informative data. Next slide. So again, because I am again explaining ReLU here, because compared to other sigmoid operations, ReLU has been widely used in convolutional neural networks. Because of this, one of the advantages is that in other cases, if you remember, so in the upper sides or in the tails, it was going flattening, and as if we take the gradient of those curve, it gives like vanishing gradients, and networks were not able to update in those regions. But if we use this kind of ReLU kind of structures, so it will always get this gradient value, and it will always update the networks. So people prefer ReLU over other activation functions. So next slide. So I need not have to explain this one. I just told it. I just kept it here because, as you remember, in that when I was telling this convolutional neural network, so there are many layers, convolutional layers, pooling layers. Those operations are being performed, and finally, when the features are learned, to then we are flattening those features, and then we are fine tuning, or we are learning even for better represented features after flattening those features and performing fully connected operations like multi-layer perceptron. Next slide. So now I'll just give an introduction. I will not go into the detail of this one, but I'll just say like how CNN has improved. Like it has started in the year, CNN is not very new, like it has started long back. But because there are various challenges, because even simple multi-layer perceptron work, our existing computer or that time computers were not able to perform, and people could not able to progress in those directions. So it is the evolution or development of those hardware modules like GPUs, and also the improvement in the open source like coding environment like TensorFlow and all those things. Even previously Cafe was used, so people could able to efficiently perform these operations. So now in the year, initially in the year 1998, LANet 5 was introduced. This you can see the network architecture. It was very simple network architecture, and he could able to perform this digital object recognition operation using 32 cross 32 image. So that was part of again this finally in ImageNet challenge competition 2012 it came into picture. So next slide. Again in 2012 another network came into picture, that is called AlexNet. So after this improvement of GPU, again it has got improvement over the previous one, and it has performed with this ImageNet data, it has performed improvement over 15.3% compared to the previous one. So what it has done is this AlexNet is much deeper than the previous network. And it is also, even though it is similar to the LANet, but it did some improvement by changing the strides and some other pooling operations. So next slide. So next in 2013, there another network came that is called ZFNet, and it did improvement over the previous network with 14.8% recognition accuracy, top 5 recognition accuracy. So this is comparatively simpler and even more efficient, and it did some changes. Even though structurally it looks similar, it did some changes in the each and every components of the network, and also it has increased the fully connected layer in this case. Then the major breakthrough was GoogleNet in the year 2014. People could never imagine this kind of deep neural network. Even though there was AlexNet, there was LANet, and there was those VGG network and all, but problem was with those network was that one problem was that vanishing gradient was always there. So as we are going deeper into the network, the gradients were becoming vanishing or very small, and then networks were not able to update. With the evolution of the network, that ResNet, so this gradient vanishing gradient problem has been solved. So I was just here giving a small, because this VGG network is normally simpler to present, or I am just giving a structural overview of these VGG networks. So here given an input of say image say 24 cross 224, it has got 2 convolutional layer followed by one max pooling layer, again 2 convolutional layer of higher size, and then max pooling layer, then 3 convolutional layer, so on, and finally it has 3 fully connected layer, and then it is performing sort max operation. So VGG network has been widely used by many of the researchers or industrial applications, and one of the important reasons why VGG network became so famous is that its source code was readily available at that time. So, and it was written in Cafe and then later in TensorFlow, so people could able to make use of it. But and one problem with this VGG network is that it has got the weights or the number of parameters are too high, that it takes very long time to compute. Like for an image of this kind of size, it takes more than a day to train a network with very large data set. Next slide. So I was telling, like, this vanishing gradient has been a problem. So now with this ResNet, after this ResNet has come into the picture, the people are not facing that level of problem, this vanishing gradient problem. So what they are doing in that, it is passing the residue, and then even though our errors are, or those derivatives of those errors are getting reduced, but because of this residual operation, it is able to perform the update operation. This one again, I'll not go deep into this ResNet architecture. This is how it is performing this residual operation. So it is feedbacking this input vector x to with this fx function, and it is avoiding this vanishing gradient problem. Next slide. So with this, actually, I'll like to end this session, first session. If you go to the next slide again, there are some references given. You can see actually there are some good courses, those who are beginner. So recently in 2020, there is a course on deep neural networks from MIT. So I have the first reference. You can actually see that is a very good course. I have downloaded some material from this one. And there are some other courses from Stanford you can make use of to understand these basics of convolutional neural networks. So this is the end of the first session. Can we have a 10 minutes break before I start the next session?
Sure, Anima, go ahead. So participants, we have 10 minutes. So probably it is, let me just stop sharing the screen now. So it is 4:10. So probably let's reconvene at 4:20, and she will begin with the second segment of the talk. Yes, Anima, we are taking the break now. We'll reconvene. We'll start again at 4:20.
Okay, yes, I'm able to see the screen. So I hope I didn't bore all of you with this last session. So this session will be completely application oriented. So mainly I'll focus on the works that we have been doing or we have done in last few years. So mostly it will be with deep neural networks. So this topic is visual perceptions for robotic applications. So before going into the details of these applications and whatever we have been doing, I just want to give a brief introduction about the term called perception. So what we understand by perception. So if you go by definition, perception is our sensory experience of the world around us. It involves both recognizing environmental stimuli and actions in response to those stimuli. So perception has got various steps or various processes like the environmental stimuli, the attended stimuli, the image on the retina, transduction, neural network processing, then perception, recognition, and action. So these all things come under perceptions. So this will be more clear if I give you a brief example. Say for example, you have gone for a morning walk, say near to a lake. So you can see there are many things. People will be around, trees will be there, water will be there. So all this comes under environmental stimuli. So suddenly now suppose you have your eyes or your focus has gone to some ducks which are playing in the water. So that attention comes under attended stimuli. So once your attention has got to that one, so an image is formed. Anyway, images you can see around everything, but you can focus on certain area. In spite of so many obstructions are there, you can focus on those ducts, and inverted image is formed on your retina. So next part is that image gets transformed into electrical signals, and that goes to your brain. So this process is called transduction. So once it goes to your brain, so brain has associated with various neurons and all those operations are being performed. So neural processing is basically done in that. So now you could able to localize, okay, the brain could able to localize that it has perceived something, it has seen something, but it's still not able to recognize. So it has seen something. And next part is how it is recognizing. So there are certain operations on that point you have seen or you are seeing, and then it is performing certain decision level of operations. So once he has decided, okay, now brain has based on his previous understanding or certain kind of recognition, these things and all, or it made a decision that, okay, you have seen a duck or you have seen lots of ducks. So now that this comes under recognition. So you have recognized. So once you have recognized, so now it is performing. Now suppose you have a phone, you have taken out your phone, and because you have seen a beautiful scene in the morning, you would like to take an image of that scene. So you have taken out that camera and you have taken an image of that scene. So you have performed an action. So what we have done, this perception, this entire process, that also we want to mimic in our day-to-day life, in robotic applications, in drone applications, or in these navigations or this car navigations and all these things. So I'll go in the next slide. So like what we know so far, what we have done so far, and what we are going to do, like what actually we know so far is, now that, okay, we understood that what we mean by robotic perception. But what we know, like, okay, we can hear that robot has been doing amazing work in factories. It is working in collaboration with human. It is also able to deliver packages quickly in warehouses. Even it can explore the surface of Mars. So it is very like great thing robots can do. But still, where exactly it is missing? What still robot cannot perform? Say, for example, robots are yet to perform a more complex task, such as preparing a decent cup of coffee. We human can do it very easily, but for robot, it is very difficult. So to perform that kind of perception, or to understand that situation, now suppose for coffee is associated with many things like dispensing the beans and finding the milk, sugar. It requires certain perceptual abilities, which are still fantasies for many of the machines. So we are heading towards that level of intelligence. Next slide. So I'll here go with, okay, given this introduction, that was all about the introduction of robotic perceptions. But I here want to focus on what in our lab, in TCS Innovation Lab, what we have been doing or we have done so far. So if we divide it into in the form of task, we can say understanding the objects around the robots, and then measuring the distance, performing certain actions like object grasping, picking, pulling, and pushing operations. So if we categorize these into some different categories, like it falls under object detection, recognition, even object annotation, semantic segmentation, then depth estimation, object grasping, even continual learning, some parts we have been working. Another is imitation learning and character recognition. So many of the terms you may not be familiar with. I'll also give an introduction of those terms while I'm explaining each and every task. Next slide, please. So one of the very previous work that we have done is we have participated in Amazon Robotics Challenge in consecutively 2 years, 2016 and 2017. The first was Amazon Picking Challenge. The second one was Amazon Robotics Challenge. So in that both the challenges, in the picking challenges, we were in 5th position in picking, and in that robotics challenge, we were in the 3rd positions. And if you see that the results, there is an image of that results. So we were even ahead of MIT, Princeton combined, and there are various like Duke. Team Duke was there, so we have performed. Even Nimbo was there, so we have performed better than those. Like not Nimbo was ahead of us, but MIT was performing as good, not as good as that in picking challenge. So that was a great achievement for us in 2017. So I'll go into that first. What we have done in that. So the main application was that now in the warehouse environment, like what is there, like there are various object has to be placed, or suppose some order has come. So with those given the list of the orders, the persons will go and pick each and every object, and it will be placed in a bin, and that will be sent to the customer. So they wanted the same operation to be done by a robot. So given the list of the objects, and those objects are placed in different racks, or then from racks it has to take out, and it has to, they have to put it into the bin, and then it has been they will they will close the bins, and it will be delivered to the customers. And next is some new objects are coming. So given those list of the new objects, the robot will have to recognize each and every object, and robot will have to place those objects into the specified locations. So next slide. So initially for this challenge, there are around 40 objects were given to us priori, and this work actually we have done in collaboration with IITK, and TCS was a part of it. So I was, that time I was also in IITK. I have just completed PhD, and I was also part of this challenge. So you can see like objects were used, like various kinds of objects were there. There are scissors were there, dumbbell were there, and some paper kind of objects were there. Some glass are there, some bathroom brushes are there, and some porous materials are there. So clothes are there, deformable objects are there, rigid objects, various objects are there. So in a total, you can say it is quite challenging to pick those objects by a robotic arm, and that too we have to recognize those objects. So here I will say, like, first part is how we are actually recognizing the objects, how we are training a deep neural network to recognize those objects. Next slide, please. So here you can see now, as I was telling, like normally there are two approaches. One is supervised approach of learning, and another is unsupervised approach of learning. So when it comes to supervised approach of learning, you need to have a outcome, desired outcome. You have to know what is the output. Now that, now suppose for example, I have an object, I want to localize that object. Localization can be done in two ways. One is by semantic segmentation, which will accurately localize each and every small minute regions of that object. Another is by using a rectangular box kind of localizations. It will give approximate locations, but it will make sure that the object is placed within that rectangular regions. So first operations what we have done is we have used this rectangular localizations of all those given objects using that time state of the art technique called ResNet. That not that no, no, that is RCNN. That was region propositional based convolutional neural networks. And underlying network that we have used convolutional neural network, that was VGG network. That VGG 16 or VGG 19 both actually we tried. Finally we have done with VGG 16. So now this part of the work that I am showing here is not about recognition, rather it is about annotation. So what we mean by annotation is that when we are training an objects, we need to know the outcome. So our outcome is the annotation, like this, okay, this is my desired location. And this is what we have achieved. So we regress our network to achieve our desired network. So we have seen like during while actually we are doing like every time, because we don't know, many times we had to redo the annotations work, and annotations work was typically done manually. So we have to manually localize 4 points. We have to draw a rectangular regions for each and every object. And again, problem is when it comes to neural networks or deep neural networks, if you give an object at one specific direction, and if you place that object in another orientations, the CNN will not able to understand it. So it has to be in a certain direction or certain orientations. So we have to make sure that while training, those objects will be trained in almost all the possible orientations or almost all the possible colors, shapes, scales. So for that, we had to annotate it manually. So it was a huge laborious job. So in order to avoid that, we have decided to develop an annotation network. So for that also, we have used RCNN framework. So what we have done is we have our indoor environment. There was 5 cameras was placed, rotating platform was there, and 5 cameras was placed in a different orientation and different scale, and then we were taking images. That stepper motor was there, and then rotating platform was rotating, and every time it was rotating, we were just taking images. And then after that, the network we have developed, that was annotating automatically. So how it was annotating automatically? For that, initially we had to do is we had to manually label some of those objects. Few objects we have manually labeled, and we trained the network for 2 class classification. This object present, object not present. So if object is present, it will give the location of that objects. So, and also otherwise it will consider as a background. So we did that work, and that work has been published in year 2018. So this is the architecture of that network. So, and also here we have used augmentation technique, like we are not annotating for each and every possible scale, but for some, let's say 5-degree orientation, we have annotated it. For others, we just augmented it by changing some transformation operations. And also we did some color transformations, because there are some cases like it was the competition was like that. Some objects will be given a priori, and some objects will be given when we were in the competitions. So it happened to be like this. Some objects colors will be different, a little bit shapes also will be different. So we try to use augmentation techniques in order to incorporate those variations. Next slide. So this is how after annotation, that learning this our annotation module, how we could able to successfully annotate. So only once it is given, this only thing is for an object, suppose one object it is getting suppose 200 of images. So and it is giving this rectangular boundary region. So only thing is we from users as we need to say that which class this object belong to, and it will automatically take and it will store those annotated images and label and all these things, and it will also create an XML file for that. So this is these are some of the images we got after annotation operation has been performed. We can see, given this, even though similar color objects are there, it is accurately able to localize the objects from the background. And even in case of transparent objects, it looks very like difficult for human eyes also sometimes to annotate it accurately. But our algorithm could able to do robustly able to do that work. So next slide. So we did it also in cluttered environment, because our original work will be on cluttered environment. So we annotated this. We used our applications to annotate in clutter also for multi-class objects. So we perform the task. And next slide. Another thing is, it is not only with a single background. We have trained our network for various backgrounds like brown, black, white, red. So various possible background we already trained it, and it could able to address all those trained backgrounds. And we compared our results with various networks, like variants of the network. We have used ResNet, we have used VZ16s, and all those things. In some cases, no, we have not used ResNet, we have RFCN. So next slide. Yes. So this is the indoor framework I have told, that camera framework. So this is also related to the previous work, but instead of annotating the rectangular regions, we have annotated the entire image, like object, an entire region of the image or object using semantic segmentations. So what we mean by semantic segmentation, for those who don't know, semantic segmentation is, now suppose you have got an image of object. So each and every pixel of the object is taken as a class. So each and every pixel of an image is taken as a class, as classes. So now the object or the pixels belonging to the objects fall under one class. So we have created another network here, and we have trained our model to perform semantic operations. And here also, likewise previously, we have also created one annotation module, automatic annotation module for semantic segmentations. So right side, you can see the framework. We have used two approaches here. One is performing semantic segmentations using the feature pyramidal blocks. So we have got RC, here we are using RCNN. So we have got so RCNNs are there. Here we have got ResNet network, actually, not RCNN. RCNN we have used in the previous one. Here we have used ResNet block, and after that we have used, for this, suppose 5 ResNet blocks are there, and instead of taking all the 5 features from all the 5 ResNet blocks, we have taken features from successive 4 feature blocks. And generally people, what they do, they will take features from fully connected layer. So now what happens, as I told earlier in the previous session, so initial layer learns certain age level of features, the next as you go it learns some eyes, nose, this kind of features. As you go higher, it learns better abstractions of the features. So people take the final layer features as an input to the decision layer. So in certain cases it happens to be like that. If we incorporate the previous layer features along with those final layer features, it improves the recognition accuracy. So here actually we did the same. We have, instead of taking the final layer features, we also incorporated previous layer features, and we combine them in a approach called feature pyramidal network. We have upsampled and those features and concatenated, and we finally given those features to the final fully connected layer. And we got even improved segmentation outcome, even better than that time state of the art method. Next slide. Yes, so this part of the work is also published in BMBC in the year 2018. So here we have compared this our work with the 10 state-of-the-art method is CNN and also PSPNet. So we can see like in terms of all those measures like MIOU, why we have used is we have also used single shot detections, and we have got these rectangular regions within this single shot detection networks. We have performed our regression operation to get the class of each and every pixels. And you can see that precision, recall, and F measures all are actually much better than the CNN as well as PSPNet. We tried it with two different frameworks. One is ResNet 50 and also another is with ResNet 101. So next slide. So now I will be addressing the next question was asked to me now, how we are using CNN for those navigation or those for those automatic driving cars. So what problem? One problem we have seen, like if we say depth is one of the very important criteria. So first is we know like 2D image will not give you the depth information. Depth is how far the object is. You can say how far. So that depth is very important when it comes to navigation or automatic driving. So here we did a couple of work in these directions. Oh, okay. Before that, I'll just like to show a video. I'll just like to play a video. I will ask Changappa, can you please show a video of that challenge we have gone in Amazon Robotics challenge?
Yeah, sure.
Yeah, you can start from the middle.
Sure. Yeah.
This work is done in collaboration with IITK TCS. You can see robot is performing manipulation operation. It is recognized. It has recognized the object. It has gone to the object. We have a UR10 robot here, and a camera is mounted on it. So it has, and also with that robotic arm, there is a suction in it. So once it has recognized the object, and also there is a camera for it is using IR sensor to predict the depth of that object, and it is going to that center of the object and picking that object. It held this held in Japan, and previous challenge was held in Germany. So this is going little so slow, I guess, right?
No, I am playing it as is, and
Okay, okay, okay. Yeah, I don't know why it is slow. Okay, I just wanted to show it actually how it has been working. You can see like difficult objects also it is able to pick. And certain heavy object, this looks like the object it is now picking is very slippery. So this kind of objects also it is able to see. Shiny objects it is able to recognize. Maybe our vision module could able to recognize. So yes, I think you can stop that
yeah, sure,
video.
sure.
Yes. Yeah. Okay. So we are in slide number 13. Okay. So now I'll tell that you have seen that robot is using a IR sensor. We are using actually sensor camera on the top of that robot. So that robot camera could able to predict the depth in an indoor environment, and we could able to reach the object. So now that question comes when it comes to outdoor environment, how accurately or like how this depth estimation will be done. There are certain cameras, like you can say you can use LiDAR sensors, or you can use stereo vision to predict depth, but it has got its own shortcomings. When it comes to LiDAR, it is very computation, very costly, and also it gives sparse data. And secondly, when it comes to this stereo cameras, so every time you need to recalibrate, and it has got its sensor errors and noises into it. So motivated from this, we wanted to go with this deep neural network approach to estimate depth using only images, using only monocular images. So now that okay, why depth is so important? One of the reason is for any, as I told, for any kind of perceptual operations or picking operation, placing operation, or any operations you can say, pushing, pulling, those kind of operations also we need, anyway we need depth information. So depth is very much important to us. Next is, so for those automatic robotic applications, we need depth. Another is for perception, planning, navigation also we need depth. So now, as I told, so we with those Kinect data or sensor data or leader sensors and all, it has got its own shortcomings. So that's why we are motivated to perform depth estimations in an unsupervised manner. So now question comes, what is that unsupervised manner? How we will do depth estimation in an unsupervised manner? Because even supervised means if we have known depth data. If we have known depth data and then we are training our model to predict depth using our data, the training data, then it is a supervised approach. But what if we don't have known depth data? Because even acquiring known depth data is also very difficult. So I'll show how we are doing it. Next slide. Next slide, please. Yes. So this is one of the work is 2018 IROS we have published. So what we are doing is now we have got we want our main motivation is to train a model so that during test time, it can given an input image, it can give me the depth map of that image without using any other references. So for that, what we have to do, during training, we are taking stereo pair images as input, and while testing, we are taking only monocular images as input. So what it is doing, now there is a concept, you know, like there is a concept of disparity. Now suppose with one eye, if you look at a point, and if you close one eye and if you look at a point, and if you close another eye and if you look at the same point, and if you mark it, it will not be in the same position. So there is a shift, and that shift is called disparity. So we are learning this shift. We are learning the mapping of that shift given left pair images as a training data. We have a, suppose given we have a training data, left pair images, and we have a disparity map. So we know the shift, we know the left pair image, then we can predict the right pair image. So we have left pair image and we have right pair image. So we are able to calculate the loss. Loss is the difference between left and right image. And that loss we are feeding to the network. So this network is like, there is an encoder network and there is a decoder network. If you can actually, you can relate it with autoencoders. Some people may be familiar with the concept of autoencoder or the bottleneck. Bottleneck, if you see, like something like there will be bigger shape first, then it has gone down as there is a bottleneck, and then it has gone again to that same big shape. So if you have a input image of dimension x, and then you are compressing, and you have gone to an encoding layer, and then again you are decompressing it, and you are going to the decoding layer, getting the same dimensional outcome or same outcome, you can say. So there is an encoder network and there is a decoder network. So we are learning the embedding. We are basically learning the encoded informations. So now that, okay, after that, we have learned this disparity, and two things we are doing here. One is we have got, we are using left pair images, and then we are predicting the right pair images using the disparity. Another is we have got sequences of images. Say we have got 3 snippet of image, like image at tth point, images at t plus 1 point, and images t minus 1 point. And then we are also using camera transformation. And then we are predicting from given this, we are training this camera, we are learning the camera pose, and given the camera pose and given any frame, tth frame or this, we can easily able to predict other frames like using. So this disparity, this camera pose loss is also given to that another network to better infer the disparity. So this is the first work that we have published in IROS 2028, in the year 2028. So next slide. Yes. So I have just explained earlier. So what we have done is, given the DiskNet means it is learning the disparity model. It takes DiskNet takes left image as input and calculate the disparity left to right or right to left. And then there is an image warping operations given this disparity. And given the left image, we can reconstruct the right image, and given the disparity map, given the right image, we can reconstruct the left image. And PostNet takes those snippets of temporally aligned left camera images and reconstruct the tth frame by predicting 6 GF pose from the source view and aligning. We are also using here bilinear interpolation for image warping. So next slide, please. So now here you can see we have compared our work with various that time state-of-the-art methods. One was monodef and SMM learners. Those were very two promising methods. And if you can visually also, you can see how better our network is performing compared to those. So So these are the scenarios, like you can see, as someone was asking me the questions like how we can use for car navigations. So we have taken our all training data are taken from those outdoor images or videos. Those are when car is navigating. So, and these are mainly taken in the daytime. So it is able to predict depth for each and every region, surrounding region. So next step, so once you know the depth, you can use those depth to segment out, or you can use those depth to predict obstacles and all these things. So next part is those inference we can perform using this accurate depth data. So next slide. Comparison. So I will not go into the details. These are the comparison we did with various state-of-the-art techniques. So in order to get the paper published in IROS. So yeah, okay. I would like to play another video on this before going to this section. There is a video on this. Chingapa, can you please play this video on daytime depth estimation approach? If you, hello? That is on daytime depth estimation approach. Yeah. So you can see, so when the scene is there, and it is also camera, it is also learning camera pose, and also it is giving predicted depth map for each and every frame. So even you can see in certain cases where there are some poles and small obstacles are there, so our depth is able to localize those, or it is able to give the depth map. So the car can, while navigating, it can avoid those obstacles. So, and road also, it has given very nice depth map for that road. So you can stop that actually. Yes. So we are in slide number 18. Okay. So now what we have done is, what we have done is earlier, we have done depth estimation for daytime images, and we have learned disparity map, and also we have learned pose. So problem is, there are certain situations when how we have to improve. Like we have seen, there are certain situations where the environment may not be same, the conditions, like the geographical areas, or the kind of, you can say, even though geographical area may look similar, but the environmental conditions may not be same. So how to address those situations or those scenarios, or to better improve the recognition accuracy with the previous one, we have incorporated introduction of, we have incorporated GAN here. So those who don't know GAN is generative adversarial networks. So that is a variant of deep neural network, but it performs generative generation operations. It generates, you can say, suppose given an input image of one type, given the conditions, it can generate image of another type. You might have seen in YouTube or something, like when Obama is speaking, or he is giving introduction to neural network, and in his own voice. So even though actually originally Obama was not there in that scene, or he didn't do that, so GAN could able to perform that kind of task. Or you can see a horse is there, so for running, so suddenly the horse changed to a zebra shape. So this kind of work GAN can do. So GAN is another dimensions, and it has got various applications into it. So we use the concept of GAN here, so that we can improve the performance while reconstructing, because we are using for reconstructing. Now suppose given the left image as input, and given our disparity map, So we are using the reconstructing the right image. Now that right image, given the right image, and then we are trying to fake, and that left image, when we are trying to fake that reconstructions using GAN, so that it can better reconstruct the image. So it has become as like kind of cyclic process. So in a way, it has further improved the performance. So this part of the work we have published in ICHCAI 2019. I'll not go detail into this one. This was somewhat similar because mainly it was done in daytime atmosphere, even though spatial change was there. So another work that we have done in next slide is slide number 20. So what we have done is we have seen mostly when it comes to robotic applications, we perform the work in indoor environment. So we just wanted to check it initially how good that network that we have done in daytime outdoor environment, how good it will work when it comes to indoor environment. And also at the same time, we did some improvement on that work. So even in daytime also it got better depth estimation accuracy. So what we have done here is that, so instead of getting only the depth map, we are also predicting the uncertainties, or we are also predicting the confidence levels. And given the predicted depth map, and given the uncertainties of prediction, each and every pixel values, so we are giving it to the network, and then that network is getting updated based on both the feedbacks. So it has further improved the performance in that. I'll just show some of the slides. I'll go directly to the slide number 23. Yes, so this is our lab environment where we have taken various objects. So initially we have trained with there was a task given to us in TCS Innovation Lab, that was pelletization task. So some boxes will be there. So we have to robotic arm will have to pick and place those objects, arrange those objects, and while to perform the picking and placing operations, of course it has to know the depth. And earlier we were using those depth sensors, so we wanted to avoid those existing depth sensors. We just wanted to use RGB camera alone. So given this RGB camera or RGB images, and we have used our trained those model. So and using this only this one from monocular images, so we are not using right pair or left pair, we are just using single monocular images, and then the model is able to predict the depth, accurately predict the depth. So given the depth, it is using region growing algorithm to segment out that region, and then because it knows the depth, the robotic manipulator is straight away going to the depth object, and then it is picking, performing the picking operations. So I would like the Chinnappa to show that video. There is a video on indoor environment.
Yes, yes. Give me a minute. Sorry, last time I realized that I was speaking on mute.
No. So this part of the work also got accepted for IRES 2020. So it is performing region growing operation of the point clouds. So it is segmented out that object regions. So once this object region is segmented, it is able to go and pick that object. This was done in fully indoor environment. Okay. So that was about indoor depth estimations, but we have shown here one demo of one object. However, we did the same work for multiple objects. Oh, I didn't show those objects, but yeah, it was done for multiple objects, for various indoor objects like bottle and glasses were there, and some other small objects were there. So I didn't show it here. Anyway, so that worked very efficiently in indoor environment. So next is now that okay, now when it comes to this automatic navigation or automatic car driving. So now suppose a person has gone for driving a car during a daytime. So when we have modeled the train, we have trained it for daytime. But what if the same person is coming back to the same regions in night time? So our daytime model was not able to perform accurately when it comes to nighttime depth estimations. So one of the main reason why above or aforesaid method did not perform well when it comes to nighttime depth estimation is that when we are calculating the loss, we are mainly based on, those are mainly based on photometric losses. And we are making sure, or this or photometric loss that has a assumption that the light source is coming, it's a constant light source. So, but in night time, it is not like this. Light sources are varying. Like there are so many street lights will be there. So sudden brightness will be there. Then there will be some places which will be partially illuminated or hardly illuminated. Some places will be very bright. So given this kind of situations, so those previous models are shown to be not performing well. So inspired by this, so we wanted to work in the direction of estimating depth for nighttime images. Yet also we wanted to make sure that our daytime model also work in certain those cases. So how the complexity lies here, how we will make both the situation to work fine, even if we know that the previous loss function will not work. So now, our assumption was why in all these cases when we are performing these depth estimations, our assumption was that given a scene, even though it is unpaired, when we are because when we are reconstructing or when we are uh, giving images, those outcome right time images, those may not be paired. So our assumption is that there are some underlying geometrical structures of a region like roads or cars or buildings, trees, lampposts. Those things are common, even though there may be some variations in the style or in the environmental conditions. So using this assumption, what we have done is we have used GAN laws here. So now we have done two works in this direction. So one work is now that we have a train model, daytime train model. So we have encoder network, we have decoder network, both are trained. So given the encoder network of daytime model, because our assumption is that it has encoded some of the features of the daytime data, so the encoding it should be same, like even though the appearance is different, daytime and nighttime appearance is different, but underlying structural attributes are somewhat same or same. So we wanted to make sure that we wanted to have a mapping, or we wanted to make similar, we want to make the underlying structure similar. So in order to do that, we had to use GAN. So generative adversarial network. So now that we have daytime image and we have nighttime image, we have daytime train model, this one. Now that we are using. So this is coming as an input. Now suppose GAN is trying to decode that. Suppose given the lifetime image, it will reconstruct that light. Given the lifetime image, it will reconstruct the right time image, the right image, and it will use the disparity. And while doing so, it will learn the adversarial losses, adversarial parameters. So here we could actually able to successfully perform, and we have shown that it is working well for daytime as well as for nighttime. So we have used a very smaller network. The network architecture is also shown over here. So there is a video of this work as well. Can you, Chingappa, can you show that video of nighttime?
Yes, yes, just loading.
Yeah. So this part of the work is published in IEEE 2019. So this is the left side is the nighttime scenario, and right side you can see the predicted depth. So in most of the cases, it is able to accurately recognize the depth, except those places where illumination is very low. So here also we have calculated this point cloud. You can see how accurately the point cloud has come. So this is all about nighttime depth estimation. So in order to validate that, as we were using underlying concept that even though the daytime and nighttime images are different, they are not paired images, but we have an understanding that the underlying geometrical informations of the images are same, like car will be there or these things will be there. And also we wanted to make sure that it has learned those attributes. So in order to do that, we have done another experiment along with this work. Next slide, please. Okay, yeah, next slide actually after that. Yeah, that what we have done is visual place recognition. So what we have done is given those embedding, using this embedding, or given this, we have found out those videos or images where places look same places, from same places we have taken images of nighttime and daytime. So, and using those embedding, we could able to recognize that it actually belongs to same places. So we did some evaluation studies and experimentations on this, and this work also part of that work that got same paper got published in IEEE. So that was all about depth estimation. So we have covered daytime depth estimation, we have covered nighttime depth estimations, we have also covered indoor depth estimations. So same is applicable using GAN. Actually, same is applicable for foggy or rainy or any kind of situations, because we are learning the underlying structures. So yes, so we are that was all about depth estimations. So next is about imitation learning. So in our lab, we are also doing a part of the work called imitation learning. So before that, I'll just say what we mean by imitation learning. What is imitation? Imitation, like we say, mimicking. So imitation learning technique aims to mimic human behavior in a given task. An agent, a learning machine, is trained to perform a task from demonstrations by learning a mapping between observations and action. So they are mostly we are doing in our lab is using visual data. So it will observe the person is performing a task, and it will abstract certain features, visual features. So given those visual features, it will learn how to perform the control actions. So now that we know, like, because imitation learning is a new area and a lot of work has to be done in these directions, so it is still far from those autonomous agents that can able to solve very complex or real world tasks. But one of the possible solution or one of the possible direction in which we are moving ahead is like to use techniques like given those images, we are abstracting the features and then we are using reinforcement learning methods. So during when we are applying reinforcement learning, so we are using, there are certain stages like this. One demonstration will be there, then environmental policies we have to learn. We have to learn the loss functions. So we have to, so these operations we will have to perform. So one small experiment we did in our lab. So this part of the work is also published in ICRA 2020. It got accepted in ICRA 2020. So this, it has got two parts. One is vision-based parts, another is that policy learning and all, given these embeddings. So here I am going to explain this part, what we have done using our vision methods, like how we are learning the representation, feature representation to perform the task. So we were motivated by one network called that attention network. There was one network called time contrastive networks. What it was doing is given a task, and when images are taken from multiple views, from different orientation, when images are taken at the same time frame, so that time frame was our feedback or our only known parameters. So now multiple frames are there, images are there from multiple orientations, and we know at the same time frame one task has been executed. So that task net or that that time contrastive network uses triplet loss, n pair triplet loss to learn the embedding. So however, we also tried that network, but we have seen that it has got some problems. We are not able to perform a small coding action that we were trying to do. So we came with an idea that instead of using the entire image or entire images of different images taken from different directions, why can't we focus on the regions where the action is being performed? The way I was telling in that initial slide, when we know we are seeing the entire environment in a lake, but suddenly our focus has gone to those ducks playing in the lake. So we also want to apply that same mechanism. So we don't want to use the entire image, rather we just want to focus on the task where the action has been performed. So next slide. Yeah, yes. So now you can see there is a pouring action. Our main agenda was to make the robot to learn. A pouring action has been performed, and the robot also will see the video demonstrations and it will perform the same task. So for that we have learned a CNN network. What we have done is we have taken features, embeddings from multiple layers. Those are given as L1, L2, L3, all those layers. And then also we have got global features. And then we have learned attention weights for every layer. Suppose layer 1, layer 2, layer 3 features we have taken. We have combined all the layer features, and also we have just combined layer 1 features with global features, then layer 2 features with global features, and layer 3 features with global features, and also we have combined all. So we did various trial and errors, and we see how this attention weights are learning, like where it is actually focusing. So you can see in the next slide. So you can see in the next slide, the left one, it is the real life videos, images are there. Different images are there. You can see when we are taking this feature map, those only initial feature map with global features, and then we are combining L1, L2 features. So we are just taking L2 features and then L3 features. So if we say when we are taking L3 features, L1, L2, L3 features combined, actually the last one, it is giving very good results on the regions. Like it is highlighting those regions where the pouring action has been performed. So another thing is, like, now when we want to train our model or our robot, so this section we cannot perform every time with this robot, or we cannot take this so many training operations with this real robot. So for that we need to have a simulation environment to train the model. So we have created, using Gazebo, our Gazebo environment, we have created one training simulation environment. And given that simulation environment, we have applied our vision model, to see is it able to learn that pouring action has been performed or not, that regions. So you can see when we are combining L1 and L2 features along with these global features, it is able to recognize the regions where the pouring action has been performed. So those features, we are just taking those features, and then we are training our reinforcement learning model to actually execute the task. So I have a small video on this also. So I will request Chengapa to show that video.
Just a minute.
So you can see here that when we had to do some changes in our policy in order to make that pouring action to perform better. So really when policy learning is not proper, so our pouring action was not performing well. But when we have improved the DDBG algorithm, so we could able to say that it is able to perform the action. In the right side, we can see that it is performing the pouring action. After, now after this DDBG has been trained with that embedding features. So it was able to perform that pouring action. Yes. Yeah, you can stop it. Yeah. So some more work we are doing in this direction. So here those are also under progress. So far I have not shown any imitation learning work here. Chandrapa, you can stop that video.
Actually, I have loaded the slides. I think that's a slide delay.
Okay, fine. Okay.
Yeah.
So now that
Actually,
here, slide
yeah,
number
slide.
33.
Okay.
Yeah, slide number 33. These are some industrial work also that we have done as a part of our work that is not related to any of those applications that I have told previously. It is slightly different. This was on palletization task when those boxes are moving in a conveyor belt, and we were asked to recognize the batch number of those objects while moving. So we have trained one capsule network. You might be knowing that this is also a variant of deep neural network. This is not same as convolutional neural network. So one of the advantage of this capsule network is that previously we were using pooling operation, like max pooling, mean pooling, and average pooling operation we were performing. So while doing so, it was as it was going higher into the network, it was actually missing the special correlations, because you were out of suppose four regions, four pixels, it was picking one of the pixels. So essentially it was actually losing those pixel correlations. So capsule network, professor actually, yeah, who has actually introduced MLP. So he introduced the capsule network, and this was one of the breakthrough in 2 years back. So this still one of the problem with this capsule network is that it is computationally very slow, as it is using routing operation. So it has got different capsule networks, like compared to those conventional CNN where we are using every node single neurons, and here it is using capsules, and each and every capsule is a kind of vector, and outcome is also like it has got various features with it. So it is performing some vector operations in it. So when it is learning those relationship between these features using different kinds of routing methods. So we did small improvement on that capsule network in order to execute this task of character recognition or batch number identifications. So small improvement was that initially when we are giving input image, that RGB image as an input to the capsule. So generally people will say only use one feature block, and then it will directly go to the initial primary capsule layer, and then it will perform routing and then go to the secondary capsule layers and all. But we did some improvement in the pre-processing stage, like in the feature modules, like feature blocks. So we use the concept of inception. Inception is also a kind of that Google network that I have told earlier. The Google network, compared to the other previous networks, it has one advantage, that it has used one convolutional operation called 1 cross 1 convolutions. So what it has done is, instead of performing a single box convolution, like one time convolutions of a big regions, it has splitted those regions into smaller parts, and it had performed multiple convolutions along with 1 cross 1 convolutions, so that it can reduce the computations and also it can reduce the parameters. So we have used the same concept here. We have used 1 cross 1 convolutions in the feature blocks, and we have drastically reduced the parameters, yet the recognition accuracy also improved. Next slide. So this is a small architectural overview of our network for character recognitions. So we have used different feature blocks, and before that also we had to do some pre-processing localization of those characters using simple vision based algorithms. And all those localization, once the localizations has been done, then we have used our capsule framework, and it could able to accurately recognize many of the batch numbers. Next slide. You can see some real life objects where batch numbers are blurry, some cases is like hardly visible to our eyes, but the algorithm is able to accurately recognize those numbers. I think yes, I'd like to stop here. Yeah, any questions, please?
Just looking at the Q&A box. I don't see any questions from the participants, Anima. So
Okay.
before I hand over the virtual podium to Prashant for final remarks, is there anything that you want to take as a concluding talk?
Actually, there are some couple of slides. I skipped it because it will take some more time. So this is like what I was telling, like this is the initial work that we have been doing with deep neural networks. Now we are actually moving ahead. We are also mainly focusing on imitation learning using reinforcement learning approaches. So these are again another big topic. So I have today's in the first session I have just covered very basic areas like neural networks, and I have hardly touched convolutional neural networks. But I will say suggest participants, because to understand what is GAN or what is CNN or what is reinforcement learning, there are very good courses already available in online, like MIT also floating various courses. Coursera, there Stanford is also offering various courses. So they can go through those courses to better understand. So this was a kind of an introduction how we are making use of CNN or neural networks, because when it comes to AI or deep learning or big data, so people cannot escape these approaches. So it is everywhere. So, and for any further queries, they can write back to me. I'm always there to help them. And another thing is like for coding and all, there are readily available TensorFlow, Keras, PyBullet, PyTorch. So PyTorch and all, everything is there. So there are some good tutorials on it. Anybody who is interested can learn very quickly and very easily.
Thank you, Dr. Anima. So, Dr. Prashant, over to you for
Yes, thank you, Changappa. Thank you, Anima. I think it was a wonderful session. I think thanks for being so patient for the last 2.5 hours and helping us go through the basics of neural networks and robotics. And in fact, it was a good sequel to the previous course lecture that we had in the data and decision engineering course. So again, thank you. I think the demos you showed were really interesting. It actually shows that how you actually take all the theory that you actually work on and use that and put that into practice. So I think those are some very interesting demonstrations of making theories and algorithms work in practice. I'm sure our participants have learned a lot, and there is a lot of things to take back from. Call out to all participants. This particular session has been recorded with the permission of the speaker, and after due editing and other things, we will put it up in a Bangalore Section YouTube channel. So people who found the lecture interesting, you will have another chance to relook at it. And for folks who have not been able to attend, they will always have a chance to go over this course because it will be there out on the live. Other things, if you have any questions as such, please direct it to the speaker. You know her name and email address, which was given in the promotion that we had done for this particular lecture. Of course, you can write back to me and Chengappa. We can always connect with the speaker. Finally, I think we from the Bangalore section and will send out a feedback attendance form to all participants. We request you all to do your due diligence in giving your critical feedback on this series, and especially places where we could improve. Okay. So with that, let me just hand over the baton to Chengappa, and with my final thanks to Dr. Anima. Thank you very much.
Yeah, thank you, Chengappa, thank you, Prashant, and thanks all the audience for your patience.
Yeah, thank you, Dr. Prasant and Dr. Anima. So, for the benefit of all the participants, please do join us on 18th of July for a session on embedded systems and IoT, lecture 2, on WSN and IoT protocols. We had already shared the registration links. Yes, Dr. Prashant was just mentioning, we would be sharing the recording at a later date on our YouTube channel. So you can always go back and have a look at this recording and also the previous sessions that we had a part of skill development program. So this note, we would be closing down today's session. Thank you once again, all of you, and have a good evening.